about using first and second derivatives to analyze the graph of a function. We've seen much of this before, but now we have lots of derivative shortcuts like the power rule, the product rule, the quotient rule, the chain rule, etc., that can make the calculations that we need to do much more manageable. So consider a mountain chain with a bunch of mountains, differing heights. The most adventurous among us might try to conquer the highest mountain in the chain. And this highest point is called the absolute maximum, or the global maximum of the chain. And some might set a slightly less lofty goal and attempt to get to the top of one of the lesser peaks. Right? And that those highest points are called relative maximums, or or local maximum. Okay. So some people call these points turning points. So we've got a couple of local maximums here. One of them represents the global maximum. And we've got a couple of local minimums. One of them represents a global minimum. So I want to take a look at the tangent line at each of the extrema in that graph. So draw a tangent line at each local max and local min. And what can you say about tangent lines at local maxes and local mins? They're flat, yeah. They're horizontal. Horizontal, slope 0, derivative 0, right? All mean the same thing. Horizontal tangent lines have slope of 0, derivative is 0. All mean the same thing. So so my conjecture is going to be derivative equals 0 at local extrema. Okay. Based on the picture that we did before. But it actually is possible to have a relative extrema where the tangent line is not flat. So look at this picture to the right here. It has a relative min. What is the derivative at that relative minimum? Doesn't exist. It's undefined, yeah. So the derivative is undefined here. So we summarize these observations in this theorem. It's proven in the book. We're not going to prove it together in class. It's called Fermats Theorem. It says that if f has a local max or min at C, either f prime of C is 0, meaning you have a horizontal tangent line there, or f prime of C doesn't exist, meaning you have some kind of a corner point or discontinuity. This point C is called a critical number or a critical point. We call x a critical number if f prime of x is 0 or f prime of x is undefined. So the theorem above tells us that the only place you can find a relative max or a min is at a critical number, a place where f prime is 0 or f prime is undefined. Okay, so let's take a look at these graphs and just identify critical points of these functions. Okay, so what is my critical number in f of x equals x squared? 0. Yep. It's the x value when the function has a horizontal tangent line or a tangent line, a derivative that's undefined. So my critical number would be x equals 0. Is it a max or a min? Min. Relative min. Okay. How about g of x equals negative absolute value of x? What's my critical number? 0 again. Why this time, though? The derivative is undefined there. So over here, my derivative was 0. In this one, my derivative is undefined. They both lead to having a critical number there. And in this case, is that critical number, does the function have a max or a min there? Max. All right, x cubed. Is there any place in x cubed where the derivative is 0 or undefined? At 0, we actually do have a horizontal tangent line. So critical number at x equals 0, is it a max or a min? Neither, right? So the only place a max or a min can occur is at a critical number, but that doesn't necessarily guarantee that there is one there, right? It's just the only place where we would go to look for one. So is every critical point an extreme point? No. Here's the two examples. This looks like a cubic. Again, we have a horizontal tangent line, but no extreme value, no max or min. Here we have a vertical tangent line, which means that the derivative is undefined here. But again, no extreme value. All right, so similar kind of exercise as the last one. We want to identify the critical point, and then look at the sign of the derivative on each side of the critical point. So it's hard for me to see the numbers on my paper. It's not much better in your... All right, so it looks like this critical number happens at x equals 3. Is it a max or a min? Min, yep. Min. And then let's look at the derivative on either side of 3. So here's one, and here's one, a couple of representative tangent lines. So tangent lines to the left of x equals 3 are positive or negative? Negative, and then after 3, they are positive. So they are, let's say, f prime less than 0 to f prime greater than 0. Does that notation make sense? They start negative. If I read it from left to right, they're negative, and then there's a critical number, and then they're positive. All right, so let's look at this one. We have a critical number here at 2. It's a min, right? Let's look at the derivatives on either side. A couple of tangent lines. To the left, those tangent lines are negative. Yep. F prime negative. And then to the right of the critical number, they are positive. All right, so here we have another quadratic. That critical point looks like it's at 3. And this time it's a max. So previous two, they were mins. This time it's a max. And if I look at some tangent lines on either side of the critical point, to the left of the critical number, what's the sign of the tangent, the slope of the tangent line? Positive. And then to the right, it is negative. F prime positive to F prime negative. Okay, and here we have some kind of a cubic and a critical number at x equals a, and it's neither a max or a min, right? And if I look at derivatives on either side, a couple of representative tangent lines, they are positive on both sides of the critical number. So f prime positive, and then we have a critical number, and then f prime stays positive. All right, so we should now be convinced of this theorem where we notice that the derivative changes sign when you have a relative max or a min. Okay, so here we had a min and we went from negative to positive. Here we had a min and again we went negative to positive. We had a max, this time we went positive to negative, and when we had neither, the derivative didn't change sign. It stayed positive on either side. So this is an important theorem. It's called the first derivative test. And it says if f prime is negative just to the left of x naught, and f prime is positive just to the right of x naught, then f has a relative what at x naught? Min. Yeah, right? Because we know that f prime negative means f is what? What does that tell us about f? Decreasing, yeah. F prime is negative means f is decreasing. So we have decreasing, right? And then f prime is positive, which means f is increasing. Okay? So it switches at this point x naught from decreasing to increasing, which means we have a relative min. And then reverse it. If f prime is positive just to the left and negative just to the right, we have a relative max. Because in this case, f prime positive, that says increasing, right? So it's increasing, and then f prime is negative, so then it becomes decreasing, so it's increasing to decreasing, relative max. And if f prime has the same sign on both sides of x naught, neither a relative min or a relative max. Because that just means it continues increasing or it continues decreasing. It doesn't turn around. So remember, if f goes from increasing to decreasing, then the point is a max. And decreasing to increasing, we have a min. All right, so we want to use the first derivative test to locate any relative extrema for this function, x squared over x minus 1. So we want to find any max and min, maxes and mins. So the only place where we might find a max or a min is where the derivative is what? 0 or undefined. So I have to find places where g prime equals 0 or g prime is undefined. So critical numbers is where we start. We set g prime of x equal to 0, and we also find where g prime is undefined. So in order to do this, I have to first get g prime. Right? So I have to take the derivative. Okay, so g prime, this is a quotient. We use a quotient rule. I've got denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. So I suppose I could simplify this. It wouldn't be too hard. That's going to become a 2x squared minus 2x, and then I'm going to subtract an x squared. So this becomes x squared minus 2x over x minus 1 squared. All right, so I have two questions I need to answer to find the critical numbers. Where is this thing equal to 0, and where is this thing undefined? X squared minus 2x over x minus 1. Okay, so if I'm going to set it equal to 0, where is a fraction equal to 0? Or with the numerator 0, yeah. It's the only way a fraction can equal 0 is if its numerator is 0. So I'm just going to ignore the denominator, and I'm just going to set x squared minus 2x equal to 0, factor it, and I get two critical numbers, 0 and 2. So those are potential places where we could find a max or a min, critical numbers. So that's one way to find critical numbers, is where g prime is 0. Another place is to find places where g prime is undefined, right? Where is a fraction undefined? And the denominator is 0. So here I set x minus 1 squared equal to 0, and we get x equals 1. So I have three critical numbers, 0, 1, and 2. These are potential places where I might find a max or a min. Might be neither, but those are, if they exist, they're going to be at one of those 3 places. 0, 1, and 2. Okay, so the thing that helps me decide whether it's a max or a min or neither is to look at the sign of the derivative on either side of your critical number. All right, so we're going to make a little thing called a sign chart. I'm going to put my critical numbers on it, 0, 1, and 2. And I want to analyze the sign of my derivative on either, in between all of my critical numbers, on either side of each critical number. So my derivative was x squared minus 2x over x minus 1 squared. So if I wrote this out in completely factored form, I'd have x times x minus 2, like that. So if you want to analyze the sign of something, we could analyze the sign of each factor. Because then you can say, well, then when I multiply them all together, I would have like a negative times a positive times a negative, and you would know what the sign of the whole expression is. So I'm going to break this thing down into its factors, x, x minus 2, and x minus 1 squared. Okay, so I've got, I'll do it down here, x, x minus 2, and x minus 1 squared. Those are the factors that make up G prime. All right, so I'm going to put these little fences here. These are important critical numbers where the sign might change. So I just put in fences. All right, think about the factor of x. Where is it negative? Where is it positive? Negative to the left of 0 and positive to right. This is like the easiest one, right? X is negative to the left and positive to the right of 0. So you just fill in all the places where it's negative and positive. All right, how about x minus 2? Where is it negative? Where is it positive? To the right of 2, it is positive, yeah. So I put positives to the right of 2 and negatives to the left. All right, and then finally, how about x minus 1 squared? Where is it positive? Where is it negative? It's always positive. Good. Can you explain why? Because I'm squaring it. You square something, it always comes out positive. So I might have broken this down into 2 factors, x minus 1 and x minus 1. The answer will come out the same either way, but it seemed efficient to me to just leave it as one positive factor. So we've always got positives here. All right, so then G prime is made up of these guys combined by multiplication and division, right? This times this divided by this. So we can figure out the sign of G prime based on the sign of its factors. So G prime, when we're bigger than 2, is a positive times a positive divided by a positive, which would make G prime positive. Extend my fences up here. Okay, between 1 and 2, G prime is a positive times a negative divided by a positive. That will come out as a negative. Between 0 and 1, we have a positive divided by a positive times a negative divided by a positive. Again, we get negative. And then to the left of 0, we have a negative times a negative divided by a positive. That would come out positive. Okay, so we now know the sign of G prime. kind of wish I could go up more. Oh well. All right, so I now know the sign of G prime, which means I can talk about G and where it's increasing and where it's decreasing. When G prime is positive, the function G, so I'll throw that right here, G of X. When G prime is positive, what's G doing? Increasing. So I've got increasing. G prime negative, I've got decreasing. And then G prime positive again, G is increasing. All right, so when a function switches from increasing to decreasing, going up to going down, what is that critical point? A max. So right here, we have a max at x equals 0. Right? And then we go decreasing to decreasing, so x equals 1 is neither a max or a min. So I'm not going to put anything there. And then when we, at x equals 2, we switch from decreasing to increasing, which means we have a relative min. So we have identified the local extremes of G. We found a maximum point at x equals 0 and a minimum point at x equals 2. So let's write that out in sort of a sentence form, because this is like, who could look at this and understand what I'm writing, right? So G has a relative max at x equals 0. And G has a relative min at x equals 2. How could you find the actual value of the max or the min? So we know that there's a max at 0, and a min at 2. Those are the x values. How could you know the y values? Just plug them into G. Yeah. You have an x value, you want the y value, you just plug it into the function G. So if I plug in a 0 and a 2, let's see, where's my original G? There's my original G. If I plug in a 0, I get 0, right? And if I plug in a 1, if I plug in a 2, I get 4 over, I get 4. So 0, relative max of 0. So relative maximum of 0. That's the actual maximum value. And a relative minimum at x equals 2 of 4. Minimum of 4 happens at x equals 2. So we got these guys by plugging into G. All right. Does that make sense? No? Okay. Uh-huh. Yep. The y value is 4.
Yes, G of X is decreasing until 0.
Yep.
And then decreases from that point on. X equals 1.
Right. Undefined at 1, so there's an asymptote. Yep. So yeah, so the continuity of it was, assuming continuity would seem confusing in this. Yeah. Let's look at its graph. Let's verify that that we actually have found relative maxes and mins. All right, so it was x squared divided by x minus 1. And we'll just do zoom 6. Yeah, we have an asymptote at x equals 1 and a relative max at 0, 0, 0. And then we have the asymptote, and so it jumps over there, and we have a minimum at x equals 2 at a height of 4. So finding relative maxes and mins is kind of a long process, right, without using your calculator. It's not too bad, but it has several steps. First, we have to find critical numbers, right? And those happen when g prime equals 0 and when g prime is undefined. So first thing you have to do is find g prime. Then figure out where it equals 0 and where it's undefined. And these are what we call critical numbers. So these guys, critical numbers, also often referred to as critical points. Okay, so they're the same thing. Then, once you have critical numbers, those are not your answers, right? Those are just potential places where you might have a max or a min. And we have to figure out, is it a max, is it a min, or is it neither? And to do that, we analyze the sign of g prime, right? So we made this big sign chart to help us figure out where g prime is positive and where it's negative, because that helps us figure out where g is increasing and where g is decreasing, and thus where it has maxes and mins. But, oh yeah, sorry, go ahead, Lindsay. We have a max at 0. Okay, I think I understand what you're asking. I think you're saying we're calling this a min, right? Even though it has a value of 4, which is bigger than this max, which has a value of 0. Yeah. So that's what we call them, local maxes and mins. And by local, we mean in its little tiny neighborhood, right? So if you were to sort of draw a little neighborhood around that point, it would be the lowest point. So it's when we move on in another section where we find global maxes and mins, this would certainly not be a global minimum, right? But it's the lowest point in its little neighborhood. All right, so there actually is another test that can sometimes be used instead of the first derivative test, which is what we just did with the big sign chart. Sometimes it's easier to apply, sometimes it's not. So you have to kind of decide which one you want to use. We want to analyze the concavity at each relative extrema. So in this case, we have a min, right? What is the concavity of the graph at that point? Up. Okay. In this case, we have a max, right? We have a relative maximum. What's the concavity of the graph at that point? Down. And here I have a min. What is the concavity of the graph at that point? Yeah, neither. Just to the left it's down, and just to the right it's down, but right at that point we can't analyze the concavity. So because one way you can define concavity is, do the tangent lines lie above or below the curve? And in this case, you can't draw a tangent line, right? So this has concavity undefined. So here's our second derivative test. First, before you can use it, f has to be twice differentiable. Okay, so that means you have to be able to take its first derivative and its second derivative. So if you have a corner point, it's not even one-time differentiable, right? You can't take a derivative there. So f has to be twice differentiable. And if f prime equals 0, that means we have a critical number, right? if we have f prime equals 0 and f double prime is positive, what does f double prime positive tell you about f? Concave up. Yeah, then it's going to have a minimum. Yeah. If you have f prime equals 0, so this is a horizontal tangent line, and f double prime positive, that means concave up, then you're going to have a min, like in this first picture. So this is horizontal tangent line, and this is concave up. That looks like cone up. Sorry. If you have a horizontal tangent line and the graph is concave up there, we can conclude you have a min. If you have a horizontal tangent line and the graph is concave down, you can conclude you have a max. If you have a horizontal tangent line, but the second derivative is 0, we can't conclude anything. We have to resort to the first derivative test. If f prime is undefined, you also have to resort to the first derivative test, like in the third picture. So again, the second derivative test does not apply to points where the derivative is not defined. All right, so now same function that we just did using the first derivative test. This time we'll use the second derivative test. And we want to find places, any local extrema, relative extrema. So that means I have to first find critical numbers, right? Because those are places where the derivative equals 0. Actually, I guess I only have to find where the derivative equals 0, not where it is undefined, because can't use it there, right? So my critical numbers, right, we already found them. We set g prime equal to 0. We found them, and we got 0, 1, and 2. But the second derivative test doesn't apply where the derivative is not defined, so we can't apply for this to x equals 1. So x equals 0, 1, and 2 are my critical numbers, but can't apply second derivative test to x equals 1, because that's where my derivative was undefined. Makes the denominator of the derivative 0. So remember, g prime of x, that was x squared minus 2x over x minus 1 squared. So the second derivative test says that you can determine whether a local extrema, whether a critical number is a max or a min by looking at the concavity there. And to look at the concavity, you have to look at the second derivative. So if f prime equals 0, we have two places where that happens. We can determine whether those points are maxes or mins by looking at the sign of the second derivative. So the first thing I have to do is take the second derivative. So g double prime would just be the derivative of the derivative. So we're going to use the quotient rule again, and we've got denominator times the derivative of the numerator, which would be 2x minus 1, minus the numerator times the derivative of the denominator. Yeah, 2x minus 2, thank you. Oh, that is a minus. So times the numerator times the derivative of the denominator. What is the derivative of the denominator? Right. 2 times x minus 1 times the derivative of x minus 1, which is just a 1 anyway. So it's going to be 2x minus 2. Everybody sees that? So I applied the power rule to the x minus 1, bring the 2 down in front, reduce the exponent, And then when you multiply by the derivative of the stuff, the derivative of that x minus 1 stuff is just a 1. So then I distributed the 2x minus 2. And then this is all over the denominator squared. Right? It's already squared, so now it's to the 4th. So I have to analyze the sign of this thing at 0 and 2. Plug in 0, see what the sign is. Plug in 2, see what the sign is, because that will tell you the concavity at those points. So I could simplify it, but all I'm doing is plugging in numbers, so it's might not be worth the effort. I can just have my calculator do all the work here. So I'm going to go to y equals x minus 1 squared times 2x minus 2 minus x squared minus 2x times 2x minus 2 divided by x minus 1 to the 4th. And I'm just going to go to my table. I'm going to put in a 0 and a 2. And at 0, the second derivative is negative. And at 2, the second derivative is positive. So write that down. So g double prime of 0 is negative 2. And g double prime of 2 is 2, which is positive. And g double prime negative means that the graph here is concave down. So I've got a horizontal tangent line at 0, and the graph is concave down, which means that it's a max. And at 2, I have a horizontal tangent line, and the graph is concave up, which means it's a min. So same conclusions that I got when I used the first derivative test. So these two statements lead me to say x equals 0 is a max, and x equals 2 is a min. So you have two ways now to determine the locations of relative extrema, the first derivative test and the second derivative test. The second derivative test can be quicker, but it is more limited in when you can use it. Okay, that you have to have, you can only test points where f prime is 0 and not where f prime is undefined. And your original function has to be smooth and continuous enough to be able to take two derivatives. All right, so next thing is that a point on a curve is called a point of inflection if the curve changes concavity at that point. Concave up to concave down, or concave down to concave up. Those points are called inflection points. Okay. To find inflection points, find where the second derivative is 0 or undefined, and perform a sign test on the second derivative. Okay, because you know when the second derivative is positive, you're concave up, and when the second derivative is negative, you're concave down. So if you ever, any place where you switch signs, positive to negative or negative to positive, you have a concavity change. All right, so we want to find the intervals of concavity on this polynomial. Where is it concave up? Where is it concave down? Where does it change concavity? So for concavity test, we want to look at the second derivative, because second derivative is what tells us about concavity. So first we need to find where the second derivative is 0 or undefined and make a sign chart. So f prime of x is 3x squared minus 8x minus 16. And f double prime of x is 6x minus 8. We set f double prime equal to 0. And we get x equals 4/3. That is a potential place where we could change concavity. Is there any place where f double prime is undefined? No. It's good to not forget about the undefined, though. All right, so x equals 4/3 is a potential change in concavity. We know f double prime is 0 there. If it actually changes sign from positive to negative, then we have an inflection point. So we should check the sign of f double prime on either side of 4/3. If you plug in any number to the left of 4/3, what is the sign of f double prime? Negative. Pick any number to the left of 4/3. An easy one would be 0, right? If you plug 0 in here, you get -8. So these are all negative. The only way that a function could change concavity for a function to change concavity is if its second derivative is 0 or its second derivative is undefined. So there's only one place. This is the only possible place where my function could change concavity. So if it's negative one place to the left, it's negative always to the left. Does that make sense? Yes. Yeah. Yeah. If there's more than one critical point, then it suffices to test one point in each interval. Because if it actually changed somewhere else in between there, you would have another critical number. The only place it can change is at the critical numbers. To the right of 4/3, if I plug in any number bigger than 4/3 into 6x minus 8, do I get a positive or negative? Positive. That means that 4/3 is in fact an inflection point because the graph goes from concave down to concave up. Right? Negatives are concave down, f double prime negative, concave down, f double prime positive, concave up. So 4/3 is an inflection point. All right, so what they asked me to find is intervals of a concavity. So I'm just going to write my answer like as a sentence. So I would say f is concave down on the interval -∞ to 4/3. And f is concave up on the interval 4/3 to infinity. So 4/3 is the place where you change concavity. It's an inflection point. All right, so interpreting graphs using calculus. This is a 3-part activity we're going to work on for the next several classes. So today is part 1. This is completely conceptual. I haven't given you any formulas, so there are no calculations to do. This is to help you wrap your brain around positive, negative, increasing, decreasing, concave up, concave down, f prime, f double prime, and how they all relate. So I've given you a picture of a graph and a bunch of questions to answer about it. And it will take some thought, maybe some discussion with your group or me. These 3 activities might be the most important 3 activities that I'll give you this semester. So put some effort into them.